Hello, everybody. Great to see you all. Great to have you here. As always, it's good to see some familiar names and faces in the chat. If you're new, great to have you here too. We're going to get started soon here with building an election simulator that's going to perform a Monte Carlo simulation to simulate a presidential election from polling data. This also is going to be a slightly new way of us writing code in the course, which is that I'm going to give you some starter code for what we're going to do. And I'm going to send a link to that in the chat. So in the chat, you'll see this link to an archive, and you can actually see, so when you unzip it, it's going to create a folder called election, and place this folder in your Python src directory. And I'm going to explain sort of what's going on with all of this. I'll say all this momentarily, but like, what is the organization of our folder structure here? And the other thing that's important is what's in the data. And you'll note that I've also started to add some like function stubs where I'm not necessarily going to write every doc string, and I'm not going to do all of the error messaging from now on. So it will, for that reason, best practices are for you to not try and type all this as we go, as well as the fact that you won't have the data, so you won't be able to run it. And so if you're following this, make sure that you go to our link in the chat, which is also on our programmingforlovers.com website, and you can access the starter code for this. So as I said, just make sure that when you unzip it, it's within your Python src directory. You should have this folder called election. I'll say that again momentarily when we get started. In the meantime, yeah, glad you can join. What did we think about the Super Bowl halftime show? Did anybody watch that? Any general thoughts? What would we rate it out of 10? It's the downside of maybe having a heavily international audience that not everybody has seen it. Yeah, I thought it was fantastic myself. I loved it. And you might not think that what we're going to do today has anything to do with Bad Bunny or the halftime show, but you'd be wrong. So there's going to be more on that here in a little bit. There's also not other course announcements. There's no other stream this week, no normal stream. So we would normally stream on Thursday. We'll be back in a week, and we'll have a normal week next week. So there will be another time. We're going to take a break after the first half of this course, and we'll have a week where we don't stream. But we have another big chapter that we have to complete after this. So, and that's my favorite of the 4. So that'll take our work for a full 2 weeks. And so keep that in mind. We'll send all the messaging for this. Make sure you're on our mailing list if you're not already, because you'll get up-to-date information about the course. And another question about our link. So I'm just going to put the link to the starter code once again in the chat. The other thing I thought I was curious about is, although we're not going to have a regularly scheduled Thursday stream, we might do a bonus stream. And I'll send some messaging about that. But I was thinking maybe we could do it at a time that would be more amenable to folks who are not in our time zone. And my question for you is, if we do a bonus stream, what would you want to see? Does anybody have any creative ideas? What would you like me to do? I've got my own thoughts, and I had asked this in our Discord, but I'm happy to hear what you think. Review and Q&A. So keep in mind, we always still have our office hours for things that are like, if you have specific questions about homework problems or our practice exercises, you're always welcome to join that. Open Q&A, I think That's a good idea too. I like the idea of doing some kind of review. One of the things that I thought might be useful is, especially now we're past the soft deadline, is, I could go through and do the homework questions or the practice exercises that we had for our initial chapter. So I'm not sure what you think about that idea too. I've got this question open on Discord, so head over there if you have more thoughts. Let us know what you think. And so look out for messaging about it. So if we're able to do a bonus stream, I kind of want to have everybody's thoughts on it. It should definitely be around programming for sure. So we're going to do more with like data analysis or, computational biology in our Great Ideas in Comp Bio course. But for now, I think that's kind of what fits with this course. That would be something that you would really find useful. The other thing I want to say is thank you for those of you who submitted our survey. That was super useful. One of the things that we've learned is it seems like a lot of folks are interested in doing a project. So that's probably something that we can only support for our subscribers to Philomath. But look out for some more information about that. And if you have, again, come to our Discord, let us know specific things that you're interested in with that, because that's something that we can take into account when we design this out. But we're definitely going to have some more messaging around that too. And I think that would be really exciting. In the meantime, tonight we're going to talk about the Electoral College. So how the Electoral College works, especially since we have an international audience, but it's also been a long time since we've had civics classes, probably for many of us in the US. But every state is going to wind up with 2 votes in this overarching process. And then they also get additional votes, at least one, that's based off of their population. As a result, this means that some people's votes count more. In other words, if you're from a state that has lower population, there are more Electoral College votes per person because your state has a lower population. As the state population increases, the influence of each individual decreases because you don't get those, each state is getting this constant number of 2 votes in addition to its population. Are there anybody out there who's a big fan of the Electoral College? Anybody want to defend it? Hard nose. No, boo. 1 yes. Now, I don't know if that's an ironic yes from Thomas or not. Well, we don't know. It's hard to assess that context there. I said that how it works is that really the smaller states have more influence. But ultimately, I don't think most people in America think that. I think that what actually happens is that only a few states matter. So there are a lot of states that we're going to know for the next probably 20 years which candidate they're going to vote for. And those states kind of don't matter. What the states that matter are the states that don't know who they're going to vote for, and it's always up in the air. And so there's probably like 5 of those. I am someone who loves the Electoral College because I happen to live in one of those states, the great Commonwealth of Pennsylvania, where we seem to just get to pick the president every 4 years, and it's really cool. It's also just a major benefit for me because I don't know, I think I've mentioned this before, but I'm a big fan of fracking. And so because of that, it means that every 4 years, this major issue comes up on a national scale, and my vote's the one that matters. So it's really cool. We'll say more about that too. So we're going to come back to analyzing all of this when we build our simulation. But I actually want to start building our simulation. So as always, please like our videos, subscribe to us. You can sign up for updates on future live streams that we're going to have, so you make sure that you get notified. BZ even noted we even have super chats on, which is nice. That's exciting. That's a big moment for us. So if you have any creative ideas for how we could use those or goals that we could establish for these, crazy things I could do, feel free to let us know in the Discord and join that if you're not there already. But I think we're ready to get started and we can start coding. So let's code. Now, we're going to have our starter code. So I've assumed that to get started, you've got your starter code, which is our election folder. It's going into Python src. And I'm going to walk you exactly through the structure of this folder, since it's an opportunity for us to build a slightly larger project. We're going to have things in a few places. So we're going to have code in main.py. And main.py is going to have just a header that says we're going to simulate the 2016 election. We could simulate other years. The 2016 election was pretty notable for its use of state polling data to make predictions for reasons that we're going to see. But I've already also added some function stubs, and they're going to have doc strings in them and so forth. So we're going to go through this here momentarily. We're going to start, though, with reading in electoral votes and learning how to parse data. So in order to do this, I'm going to show you that in our data folder, we have a few different files. So the few files that we have are going to contain two things. So we have 4 files. They contain really only 2 things. The first thing that they contain is a collection of an assignment. And if you look at this, you know exactly how we're going to read this in, because we've worked with this a bit before, where I know that I have a dictionary of sorts that's mapping state names to number of votes. So in the 2016 election, Alabama got 9 votes, Alaska got 3, and so forth. The other parts of the other data sets that we're going to have are going to represent polling data at different points in time. So the first set of polls, we captured this polling data. They're available online. The first collection of polls are relatively early on, like a few months before the election. But regardless of all 3 of these files, they'll have the same format. So you pick your favorite state. We all love Florida. And so at this point in time in 2016, the state of Florida said 52.44% of people were polling for candidate 1, 47.56% were polling for candidate 2. Now, it just so happens that candidate 1 is Clinton, candidate 2 is Trump in this picture, and it's redundant to provide both of these pieces of data. Like one is just 1 minus the other one, or 100 minus the other one, so these are percentages. And the other thing that you might wonder is, well, what about all of the other like independent candidates or other party candidates like Gary Johnson and Jill Stein and all the other skeletons from 2016? We're not modeling them. So they're not included as part of our model. We're just assuming a 2-person race, and that sort of makes sense. So these have been re-normalized to indicate, of the people who are not voting for the other candidates, what's the breakdown in terms of polling. And so you see this differs from one state from another. Some states have pretty significant discrepancies in favor of one state versus one candidate versus the other, but there are enough close to 50% that presumably this is going to make for a simulation where we're going to run this 1 million times, and then we're going to add a little bit of randomness to this, and then it will allow us to see over those 1 million simulations what percentage of the time does each of these candidates win our simulation. So when we look at the files, and I should say the next set of data are from the conventions, and the file format is the same, but they've changed a little bit. So when you look at the early polls for Florida, it's 52.44 for candidate 1. Then you look at the conventions where the candidates are sort of nominated by their parties. And so this has changed a little bit. And then we look at the debates where they debate each other, and we get yet another collection of numbers. So these are also aggregate numbers that we produced based off of averaging some polling data that were captured from around this time. So we could get even more granular with this and look at individual polls, but I don't think we're going to need to in order to make a reasonable simulation. So we can start on this now that we understand how the data are formed. And I think it's clear what we want to do with electoral votes. We want to read this in and store it as a dictionary, mapping states to integers. And for each of these, any of these other data sets, we want to read this in and map state names to the percentages for, and as I said, this is somewhat redundant, so we can just pick candidate 1, and candidate 1 will have the percentages associated with each state. As a result, we can subtract that from 100 if we are interested in candidate 2's percentages. But if we look at our electionio.py, this is where all of our parsing code is going to go. And rule number 1 of parsing code is that it usually is very boring. And we are fortunate to live in a world of AI in which if you could communicate to the AI that I know, here's what the data form is going to take in my file, and here's what I ultimately want from this, you understand the problem. So this is a natural type of question that in reality these days, we're not going to write a whole lot of parsing code by hand probably, but I want to show you how it works so that you know it's not a mystery. And it's just as much programming as anything else that we do. It's also not as thrilling as designing some cool algorithm or timing it or seeing that it's fast or applying it to real data. All we're ultimately doing is making a connection to our file and reading this in. And it's a big part of why I've given you the doc string for what we're doing. And I've already put the type hints in here. And I've already done a little bit of error checking. One of the things I want to point out is, let me just point you how this is going to work. We take the name of the file as a string. That's going to be our input. We're going to return, this is a file that's going to process the number of electoral votes for each state, so it's going to read in this electoral votes file. And that file could change, so I'm not going to assume that it's called electoralvotes.csv. As we saw in a previous code along, the number of electoral votes changes from year to year based off of population. And so when I read in that string, what I want to produce is this dictionary mapping state names to numbers of votes. So one of the things that I will do then is I want to make sure that the file name doesn't have length equal to 0. That would be bad. So it needs to be a valid string. The other thing I want to check though is I want to ensure that the user actually inputs a string, because if they tried to input the number 14 or something, who knows what would happen if I try to access a file that's just named integer 14. That would be bad. So I want to protect the code a little bit from a user doing something like that, whether by mistake or intentionally. And here's an opportunity for me to show you something in Python for checking that called isInstance. So isInstance is a great Python built-in function that takes a variable and it takes the type and it returns true if the variable has that associated type. So if file name is a string, then this is going to return true. And in that case, we want everything to be okay. If it doesn't return true, so it returns false, that means the file name is not a string. And so that's what we're checking here. If that's the case, I want to produce a value error and say that, well, you needed to return a string here. So to write this function, I've just got a stub here for now. The first thing that we should do is probably declare the dictionary that we want. And I'm going to call that thing electoral votes. So electoral votes is a dictionary of strings to ints. And it starts off as an empty dictionary. And then way down here, eventually, that's what I want to return. So I'm going to return my electoral votes dictionary. And then in the meantime, I need to do the processing. So I've declared the dictionary that I want to return. And in the meantime, I want to parse in the file contents. In order to do that, the first thing that I want to say is I'm going to need to, so if you look at the file itself is a comma separated file. So that's what CSV stands for. The comma indicates the separation between the name of the state in this case and the value. So for each line, what I would like to do is read out the line, split the line at the comma, and then access whatever occurs before the comma and whatever occurs after the comma, and that tells me the state name and the integer. So I'll import CSV at the top of the file. You see this import of the CSV module, which just makes working with these comma-separated files super easy. And once I've done that, then that's going to allow me to call functions from within it. And so how I will do this is to say there's a special way that you will often open files, especially if you're reading them. I want to open the file name indicated, and I want to tell it that I'm reading. So when you open a file, sometimes you might want to write to the file. So I'm going to give it the string R, and then I have as file. So this is a fancy way of saying get a file object called file from the file name. So if you open that file, and this assumes everything has worked, you've read it, you've assigned that you want to be a reader of that file, and now we obtain this object, which we're going to talk about object-oriented programming soon. But you wind up with this object that is a file object, and I've just named it file. That means that I'm going to pass this file object into a special reader object that comes from this CSV package that I've imported, or module. And so what I will say is I'm going to call csv.reader of file. And what that returns is a list, one line per element. Okay. So when this function returns a list and there's one line of the file for each element of that list, well, I want to call this, a natural thing to call it would just be to call it lines. So this is a list where each element of the file corresponds to a single line. Each element of the list corresponds to a single line of my file. Each element in lines, then, you might say, is what exactly? So because I've called csv.reader a file, fortunately Python has gone in and it will split everything that all the elements, every time it sees a comma, and it's going to separate these out. So what I will say then is lines has one line per element, but each element in lines is a list of strings. So this is our first small indication of a list of lists, which is something that we're going to work with very soon whenever you need to represent like a two-dimensional array, which we will need for building cellular automata. You're going to need a list of lists. But for now, I want you to think of, well, this is giving you a list of lines, and each line itself is a list of strings. So the first element, like lines of 0, for example, is the string Alabama and the string 9. So I'll say e.g. lines of 0 is the list Alabama and then the string 9. And that's really close to what I want. I want Alabama, that's the state name. I also want 9, but I don't want it as a string, I want it as an integer. So what I can do then is we range over all of the lines, and for each one, parse the state name and the number of votes. I know how to range over a bunch of things. I know how to range over a list. This is ultimately just a list, and I'm going to range for line in lines. Line is, as I said, a list of strings. So I know what line is. It's going to be the state name and then the string corresponding to the number of votes. The first thing is the state name, and that's line of 0. So we said this initial element is this and this, so that would be whatever my current line is of 0. The number of votes is very close to line of 1, except for one little thing. And that one little thing is I need int of that string. So I need to make sure that I convert it to an integer, but we have this typecasting that's built into modern languages, including Python, that will allow us to just say, I've got a string, but I know it's a string of 9. I can easily just convert it to an integer with an int function. So far, so good. And then what we notice is this function complete, because I've read in the file, I have a list of lines, then I've ranged over that list of lines, and for each element, I know that the first element in that list is the state name, and the second is this string corresponding to the number of votes. So I'm very close to being done. The only thing that I need to say then is, I shouldn't go too far down, let's assign the dictionary key and value. And here I simply say that the electoral votes for the current state that I'm looking at, which is state name, is equal to number of votes. And that's that function complete. So now that the function is finished, we just need to write a comparable function to read polling data from file. So remember, as I said, if you look at one of our files, it's very similar, except that it has 3 elements on each line. So we have the state name, and then we have the polling percentage for candidate 1, and then the polling percentage for candidate 2. So our code's not going to be quite identical, but it's going to be pretty similar. It's going to take a file name as input, and that should be a string. And I should make sure that it's not empty, and I should make sure that it's a string. So I'm still going to have this same error checking here. And then I want to return a dictionary of keys, which are strings, that map to floats, which in this case are polling percentages. So you might wonder, well, I'm only going to have one polling percentage, so I'm mapping a state to one candidate's percentage. And that's right, because this will just make things easier to work with. So if we ever want the other candidate's polling percentage, I can just subtract it from 100. So our dictionary is going to map Alaska to 47.216 and so forth, Arizona to 50.473, because you add both of these up to 100. So that it's easy to get one from the other. To implement this function, I'm going to follow the same sort of parsing. So I want to still have my with open file name R as file. I still want to declare my dictionary that I want to work with. And really, that's probably the first thing that I should do. So let's call that dictionary candidate 1 percentages. And this is a dictionary that maps strings to floats. And it's an empty dictionary. And eventually, that's what I'm going to return. And in the meantime, then I'm going to open the file. So open the file for parsing. And here's where I say with open. And I look at what my code says before, which is with open file name R as file. Okay. Now that I've opened it, I want to say, let's set the lines in the file equal to what happens when I call csv.reader of my file. And now I need to just range over the lines and parse each one. So this process works just as before. For every line that I see in this lines, which is a list of collection of things that we're thinking of as the lines of the file, each individual line, as we've seen, is just a list of strings. And so when I range through that, I'm going to have two things. I'm going to have line of 0 is the state name. Line of 1 is candidate 1 percentage. And line of 2 is candidate 2 percentage. So let's set this appropriately. I'm going to say state name is equal to line of 0. That's what we saw before. The current polling percentage for candidate 1 is going to be, well, it's line of 1, but it's a string. So everything's getting parsed in as strings, and I just need to convert this to a float. And we can ignore line of 2, since we can infer it from candidate 1 percentage. And now it's very tempting to say, all right, well, we know what we're going to do. I'm setting candidate 1 percentages of the current state name equal to the percentage that we care about. And there's one little thing that I want to do here, which is when I look at the polling data, all these numbers are between 0 and 100. What I would love to do is to just make these normalized to occur between 0 and 1. So I need to convert a percentage, like 54.54%, to a number between 0 and 1. But that's easy. I can just divide whatever I get as my percentage, that's why I call it a percentage, by 100. At the end of this process, we return candidate 1 percentages, which makes sense. Our dictionary is complete. We range over all the lines. We set the candidate 1's percentage for the current state, and then we eventually return that. We should probably make sure this works. So I'm going to save my code, and I'm going to go into main.py. And in main.py, I've got a blank def main. I've also got my if name equal main check at the bottom. And I've got some code, some functions with docstrings and type hints that I'm eventually going to write. But in the meantime, I could just go ahead and make sure that everything is working. So the first thing I want to do, and we've seen this very briefly before in the course, but we could ensure that we can actually access the files, or the functions, I should say, from the file that we were just working with. So Python by default is not going to allow me to just go in and call either of these functions like read polling data or read electoral votes that I've just written. I need to make sure that I import them. So that's not too bad. One of the things I could say would be to import election_io. But we know what specific functions we want to import from that. And so I'm going to say from election.io, we're going to import exactly what we need, which are the functions, we call them read electoral votes and read polling data. So now that I have that written at the top, anytime I want to call either of these functions, I can just call these functions as if they're in here. So it's nice because it separates things out. I think only the input-output stuff lives in this particular file. Only the stuff I'm running with respect to the simulation itself and actually calling my code and making it execute, all that's in main.py. This is another thing as we go through the course you're going to see a lot of. It is a strong thing to do. In the same way it's a strong thing to do is to separate your code out into functions, it's a strong programming habit to make sure that you have code in appropriate files where each file sort of is devoted to one overarching task, like helper functions or input-output or visualization of some kind or these sorts of things. So we'll eventually see that we will probably keep only the critical functions and things related to running the code in main.py, and everything else is going to go into a separate file just so we don't wind up with 500 lines of code in one file. Now, we have 3 functions here, and before I even show the functions, where we're building on what we've just done with writing code and doing file parsing with election.io, we're now ready to actually make our simulation. And we have quite a few functions to write. So here's my opportunity. We're going to have a lot more questions for you here shortly. But it's an opportunity for me to ask you a question, which is, what's the first function? If I'm trying to simulate the election, what is the first function that I should write? Where should I start? And this is a much more general question, which is like, when presented with a big simulation or model that we want to build, where's the natural place to start building that model? Anybody have a thought? Do you forgive me for liking fracking? Claudio says main global task. I love that. And one of the things that we're trying to communicate in the course is we think of everything in terms of big picture problems, but in particular stating things in terms of inputs and outputs. And we want to solve the problem, which is to simulate an election, right? And we want to, in other words, we want to simulate the election for 1 million trials, and we want to think about all of the data that we're going to need and what is it that this election really needs to know in order to perform that simulation. So I will often, almost always, when we're writing code, I will start with my highest level function, meaning the one that solves the problem that I care about. And so that's the first function that appears in our starter code. And I'm calling it simulate multiple elections. And you will see that you can be grateful. I suppose I could have done a lot more error checking here, but I've written out all of our parameters and all of our returns because now we're starting to see this transition towards functions that take in a lot of parameters and return a lot of things and that do more complicated things. That's great. But let me specify what each of those inputs needs to be. So if I want to run multiple elections that I'm simulating, the first thing that I need is the collection of polling data itself. So I need to know this map of keys that are state names to polling percentages for one of the candidates. So that's the first thing I need to know. The other thing I definitely need to know is what's the number of electoral votes for each state. So the dictionary that I've read in, I need to pass that to the function too. And then I also need to ensure that, well, I know how many times I'm running my trials. So am I going to run this 1 million times, 10 million times, 1 billion times, 1,000? And then the other thing I need to know is the margin of error of each poll. So if you've done the reading that accompanies this on our Programming for Lovers website, we get into what this is. If you're a little concerned by this, you haven't seen that, that's okay. I'm going to explain how the margin of error gets factored in, but this is saying essentially how confident we are in this poll based off of how many respondents there were. So how close we think we probably are to whatever the true polling value might be. All that stuff is important as input. And then as a result of this, I want to return a tuple of 3 things, which might confuse you because I'm going to simulate a lot of elections. You think, well, how many does candidate 1 win? And how many does candidate 2 win? But there's a third possibility. And the third possibility is, well, what are the probabilities of each of the 2 candidates winning? And what's the probability that there's going to be a tie? Meaning, how many of the simulations on average, when we average the total number of these by the total, how many of those result in a tie? And so what's the likelihood when we divide by the total number of simulations that a tie results? So we'll start with this function, and that might seem intimidating. I know a lot of times when learners come to programming, they're interested in thinking about the specific details. And you think, well, how do I get margin of error integrated into my code, and how is all that going to work? And I want you to remember, one of the benefits of coding in the way that we do it in the course is that I encourage you to be as lazy as humanly possible. And here's an example of what I'm getting at, which is that if I want to simulate multiple elections, well, after doing some error checking, the first thing that I might say is to say, how many times did I win? This is the same thing that we saw when we were simulating a casino game. So how many times did I win would be like, how many times does each candidate win? So I'm going to establish a win count for candidate 1. I'm going to establish one for candidate 2. And then I'm going to have a tie count, which is the number of simulations that we run where we see a tie in the Electoral College. Now, then the question is, these hold the number of wins for each outcome. What we ultimately want is the ratio of these counts to the total. So if I'm establishing this as an estimated probability of each of these outcomes, at the end of this process, what we're going to return is 3 things. I'll say probability 1 is equal to win count 1 divided by the number of trials that I have. Probability 2 is equal to win count 2 divided by the number of trials that I have. And then probability of a tie would be the tie count divided by the number of trials. And so at the end of this process, we're going to return those 3 things. So we're going to have probability 1, probability 2, and probability tie. And you've seen this before. We haven't used it so much. But when I first introduced functions, you'll remember when you return multiple things, I said, remember this at the time, and you didn't even know what it was maybe. But we said when you return multiple things, those get returned as a tuple. So you'll note I specified this in the type hints to the function where I say I'm returning a float, and a float. So 3 floats corresponding to those 3 estimated probabilities of the candidates winning and a tie. So that's the easy part. The challenging part is to range over all of the simulations and actually perform the simulations. And so in the meantime, we need to run the simulations. And you think, well, here's where the tricky details are going to live. But again, thinking about being lazy, what I want to do is something where I don't care about the index of this. I want to run something where I'm ranging over the total number of trials. And then for each trial, now I'm going to run an individual simulation. So when I run the individual simulation, what I want to call is simulate one election, whatever that means. When I simulate that election, the question is, what is it ultimately that this function should return? And I could scroll down and show you, but my question for you is, what is it that this function should, what is it that it should return as a result of this? I haven't even specified yet what its input should be, but I do want to run the simulation, and then I want to capture something from it, right? And so as a result of this, what should I get? Couple good answers here. One good answer would be, and I think this is completely reasonable from Remy, which says who won. So this was going back to what we did with craps. We said when we ran a single simulation, did we win or did we lose? So it's like a Boolean output. We could do the same thing here, except for this weirdo contingency that nobody wins. So we have 3 different possibilities. And as a result, I could return I could return 3 different integers, but that feels a little clunky. And so instead, I'm going to take the other idea I saw, which is good, which is to return the number of total votes from this Electoral College. As a result of the simulation, each candidate is going to get some number of votes out of the total. It's how many did they get? So I'm going to have this function return 2 things. The number of votes for candidate 1 and the number of votes for candidate 2. And by this, I mean within the Electoral College. So the Electoral College has like 538 total votes. So this is after simulating the states. How many of those smaller collection of votes based off of the state results does each of the 2 candidates win? And once I do that, then I can say, and notice I haven't specified the inputs to the function yet, but I will. I'm going to say who won. And now it's an easy check, right? I can say if candidate 1 got more votes, then good job by candidate 1. They're going to have their win count increased by 1. I think I have an extra little space there. Else if, what I did with the indentation here. Hopefully it's going to be okay. Okay, let's try that again. No. Else if votes 2 is bigger than votes 1. Then I'm going to say, let's set win count 2 plus equal to 1. So candidate 1 won. And then we're going to have an else, which is our most dreaded imaginable case. And in this case, I'm going to increment the number of times that I've seen a tie as a result of this simulation process. And then that means that the entire election is a tie. Does anybody even know what happens? It's like a trivia question, as well as genuinely what happens. I'm a bad citizen. Congress intervenes. I had to remind myself of this today, so I did look it up. I was like 98% sure. But yes, correct answer is it goes to the House of Representatives for the president. And I think the Senate elects the vice president. So there's one of each of the houses in Congress does an election, and each state gets one vote. So then it's not even all the representatives get a vote, it's each state gets a vote. Oh, and so that hasn't happened since 1824. And of all the weird things that we've had happen in elections in America, that's the one we haven't happened. So I just assume that that's probably going to happen soon. Nevertheless, so that will be factored into our simulations. We have these three possible different outcomes, and we have our function is now complete. And what's nice about it is I passed all of the work into simulate one election. But here is where I'm going to use this as an opportunity to say, well, what is it that simulate one election should take? And I could think through this, but the natural way of thinking about it is that this function only really used one parameter. The only parameter this used was number of trials. So as a result, I know that simulating one election needs the polls, it needs the electoral votes, and it needs the margin of error. So I'm just pulling away one of my parameters, which is num trials, and I'm pushing the rest of my inputs to my high-level function into a subroutine. This is something you're going to see a lot. It's just good coding practice, and it makes it easy to think about how it is that we work with our inputs. So in this case, I want to make sure that I keep those parameters in order. I'm going to do polls, electoral votes, and margin of error. So let's give it polls, electoral votes, and margin of error. And when you look at my function here, you'll notice that I need to make sure that those parameters are the same ordered, but they are. And now we've written our function. So we range over the total number of trials, we simulate it once. It's the same overarching idea that I saw with simulating a dice game or any casino game, where we run a bunch of trials, we see what happens each time, and then we look at the average behavior. And so it's the same thing that we were seeing in terms of this overarching idea of Monte Carlo simulation, simulating the same thing a bunch of times and just taking the average. That's it for this function. I need to maybe come back and make sure I don't have any indentation concerns here, since Python's strict about that, but I think it'll be okay. In the meantime, I want to simulate a single election. So I passed all this work to my simulate one election subroutine. And we have a doc string written here. We have our type hints. We're going to take our polls. We're going to take our Electoral College votes, mapping state names to integers. And we're going to take our margin of error of all of our polls. And then we're going to return, well, we know what we're going to return, which is the number of votes for each of the two candidates when we simulate the election. So we do some basic checks, and then we want to implement this function. And now we get to satisfy all the fellow Electoral College fans, which is to implement this idea of how do we simulate an election from state polling data and then obtain a final result from this. So the first thing that I'll do then is I'll declare a couple of variables. And these variables correspond to the number of college votes that each of the two candidates receives. So that's what I know I'm eventually going to return, which is going to get returned as a tuple. So I return those two things. And in the meantime, well, I'm simulating the election. It takes place over all the states. So I need to range over all the states and simulate each one. I can easily get the states because I assume that I've read in the data that I care about, which are the polls and the electoral votes. So I can range through all the states by, I guess I could range over polls, or I could range over the other one. The state names are going to be the keys of either of these. So I could go in either direction. The way I'm going to do it is to say, I care about the state. I also care about the polling value. That's going to be really important. Like, what is candidate one's polling percentage, which is what this dictionary is going to store. And so I'm going to say we're going to range over state and polling value in polls.items. Remember, that's our syntax that we use whenever I want to range over both the keys and the values of a dictionary named polls. When I do that, I can definitely need to also access the number of Electoral College votes in the current state. So that will be important. I can easily get that just by saying that the number of votes is equal to the Electoral College votes of the current state that I'm working with. So the current state is given by the key of this polls dictionary that I'm working with. Now we say we need to perform the actual simulation. One of the things you might be worried about is, where's the randomness? We said we were doing Monte Carlo simulation, which requires us to use pseudo random number generation in order to simulate a result. But we haven't added any randomness to this yet. And here's where I'm going to pass all that work to the lowest levels of my code, which is something we're going to see as we continue to program larger projects, which is a lot of times the gritty details are going to lurk deep in a subroutine, which is good. It means I can focus on the things that are not gritty details in advance. In this case, that subroutine that I care about is to say, well, I've got the polling value that I'm currently at. So if I go back and I look at my data, for example, I think I was looking at like Alaska before. So if I look at, I'm currently looking at like Alaska as the state name, and then its polling percentage is 0.472, something like that. So this maps states to values in that way. When I go to main.py, it would be tempting to just say it wouldn't be a random simulation, but I just would know that, well, I could say which of these two values is bigger. But the idea is this may not be the true value. It may be the case that candidate one has greater than 50% of the true number of votes in that state. So what I want to do is I want to randomly adjust each of these percentages in a random direction. So sometimes they'll go up, sometimes they'll go down, and I need to make sure that I'm doing that in a fair way, but I'm allowing randomness to run its course. And so to do that, I'm going to pass that work to a subroutine. And so I'm going to adjust the poll number up or down by calling a function that I'm going to call add noise. Noise might not be the best way of putting it, but the idea is to push this candidate one percentage up or down based off of the effects of randomness. I could talk about how that works, or I could do the strong computer science thing and just push it to a subroutine. So I'm going to say, take your current polling value, which is candidate one's percentage, current polling percentage in that state, and just sort of push it in a direction. And here's where the margin of error is going to help with that. So when we write that subroutine, we'll talk a bit more about this. I don't want to focus on it too much for now. I just want to point out that, well, we are essentially we're using a couple of these parameters to simulate one election. We're using the polls and we're using the electoral votes. And now we're going to take this final parameter and just push it to the bottom level of our function hierarchy, so to speak. And that's going to be in this add noise subroutine. However it works, right? I want you to note too, presumably we could change how this function works, and it's not going to change the rest of the code. It might change the results. But at the end of the day, I'm just adjusting the poll by adding some noise to the current value. Then when I do that, what I'll say is, as a result, which candidate is simulated to have won the state? And if we look at, for example, candidate 1 in Alaska at 47.21, when we add the noise to it, it may have moved their percentage up, it may have moved their percentage down. most of the time they're going to lose the state because they're trailing in the polls. But in some of these simulations, the add noise is going to bump them over 50%, and then we're going to simulate that they have won the election in that case. So when we do this, all I have to ultimately do is say, is it the case that the adjusted poll is bigger than or equal to 0.5? And if so, then I'm going to say candidate 1 wins the state. And then in this particular case, I'm going to say college votes 1 plus equal. And here's where I need to say, well, each state gets a different number of votes, but I've already figured out how many votes does the current state receive. And the current state receives number of votes. Okay. So as a result of that, in the other case, we're going to say college votes 2 plus equal num votes. So this is the case where candidate 2 wins. And you say, well, what happens if they're equal? The likelihood of these two values being, like this value after it's adjusted, being exactly equal to 0.5 is so tiny that there's no reason in considering the case of a tie. So I could do this or I could do this, and it's not going to impact the end result of our simulation greatly. All that remains then, hard to believe, but we've done most of the simulation. We just need to write our add noise subroutine. So here's where the gritty details are going to lurk. And as before, we've got type hints for you. We know that we're taking the existing polling value. That's the value in the map. We're taking this margin of error that's telling us how much we think we might acceptably be off by. So I'll say a bit more about that here shortly. And then we're going to return a float. And that float is going to be, well, it's that adjusted polling value for candidate 1 after adding, and I should say, or subtracting random noise. So when we add the noise, it doesn't necessarily always going to increase candidate 1's percentage. Sometimes it'll decrease it. And so the question then is how to represent that. Here's where I need to actually say what the margin of error is doing. And I'll put that in a comment. So the margin of error means, well, I should say it is the value y such that there is a 95% chance of the true value being in the range between polling value minus y and polling value plus y. And I'm going to actually just write this in the fancy way by saying we're looking at this interval of the polling value minus y up to the polling value plus y. So for example, if the margin of error was 5%, and we look at our example of Alaska again, what this is saying is at this point in time, we're estimating with 95% likelihood the true polling percentage is between 42.216 for candidate 1 and 52.216. So we're adding or subtracting 5% in each direction to say that the true value is somewhere in that range with 95% probability. So that means there's some reasonable chance that this actually is above 50%. Now that's for a value of margin of error of 0.05, which is a standard value that they use in polls. But then the issue becomes, how do I generate a number? What I want is I want to adjust the poll in a random direction so that the adjusted value has a 95% chance of being in this range, and that might not be clear at all. And here's where we get to use our favorite thing in the course, which is math. So I'm going to show you a picture. I have a folder of my own called images, where I'm going to show just a couple of demos here. And one of the things that we want to work with, or we want to work with here, is the standard normal distribution. So the standard normal distribution has this property that 95% of the values that you would generate from it. So technically, you generate any number from negative infinity to positive infinity. But the likelihood that it's outside of the range -3 to 3 is pretty tiny. And so most of the time it's in this range. In fact, 68.3% of the time it's between -1 and 1. And 95.4% of the time it's between -2 and 2. If you pick your favorite interval, like 0 to 1, you say, what's the likelihood it's within that interval? Or 0 to 0.7. It's proportional to the area underneath this curve. So when we look at the bell curve, that's what it's meaning. It says your favorite interval of values, the likelihood of something being chosen, because this is a random number that's getting chosen, the likelihood that that random number gets chosen within that interval is the area underneath the curve according to that interval. So 95.4% of the area under this curve in total lies between -2 and 2. That 95% should be familiar. So we said we wanted in main.py, we wanted there to be a 95% chance of the true value being in the range polling value minus y to polling value plus y. So y here is the margin of error. We get the standard normal distribution. So standard normal, so a number I should say, a random, because we know there's no such thing as a truly random number generated by a programming language, but a pseudo-random number generated from the standard normal has a 95% chance of being in -2 and 2. So that's like, we're in the same ballpark. These are very different values, right? But at least we have a 95% chance of it being in some range. The first thing I'm going to do then is to say, let's generate it. So we need to import the random package, as you might have guessed, since we're eventually going to make it to random number generation. And once I've imported that package, I'm going to call a function called Gauss. So Gauss is our old friend from the quick trick that we saw for summing the first n positive integers. And if you give it an input of 1, this is going to give us a Gaussian or standard normal or normal distribution with a standard deviation of 1, which is what we want. So this gives us a 95% chance of being in -2 and 2. Then what I want to do is to say, let's divide it by 2. And you might say, why would I do that? Well, now it's a 95% chance of being in what? -1 to 1. So far, so good. And now that I've got that, I'm like, well, that's close to what I want, because actually what I'm kind of interested in is -y and y. So y here is the margin of error. And so I'm going to say x times equal to the margin of error. And now it's a 95% chance of being in negative margin of error to positive mo. I like that. Okay. And that's really close, right? Because here is what we want, and we just need to add the polling value. So we're going to say return the polling value that I currently have plus x. So to get in the range we care about, add the polling value. So it's going to be in polling value minus MOE, polling value plus MOE. Okay. So that's our function. We can add noise to any polling value that we want. And notice it's a function also of margin of error. We've written all of our functions. We've got all of our input and output stuff. We've done our parsing. So it's just a matter now of running our simulation. We get to do the fun part. BZ says it's the anxiety-inducing part. There's no reason to have anxiety. Our simulation's going to work, I think, I hope, unless I mess something up with some of these indentations here, which I don't know why they got off. Okay, but we can simulate this. So the first thing we probably should do, honestly, is just to make sure that our parsing code is working. Let's say polls is equal to, and really probably the first thing I should do is, like, when I read in the data, I probably should say, what are the two files? So I'm going to have an electoral votes file, electoral vote file. And here's where we need to access the data folder and then look at the associated file within it. So I'm going to say data / electoralvotes.csv. And then I'm going to have a poll file. And this function is going to read in from data / early polls.csv. And once I've read each of these, then I can call them. So let's read in polling data from poll file. And let's read in electoral votes from electoral vote file. And I'll say files read successfully. And let's just do a sanity check. And that's going to be, let's call print electoral vote file. And we're going to print poll file. Okay. I think I realized what my issue was, which is that I've somehow got this mysterious space here. Is that going to fix everything? No? Okay. I don't know. Somehow the indentation of my code just doesn't, VS Code just doesn't like me today. I'm terrified. I'm the one who should be anxious because I feel like this must mean that I've got something wrong. Like electoral vote file is equal to this string. Poll file is equal to this string. So far, so good. Well, let's see. The worst thing that can happen is I get an error. Maybe I will. So I'm going to pull up a terminal. I'm in SRC. And let's navigate into the election folder. Make sure that everything here is saved. And I feel like I'm marching off into the abyss, but we're going to cd into election. And I'm going to call Python 3 or Python if I'm on a Windows machine of main.py. Unindent does not match any. Thank you, Python. Okay, so Python is angry at me. And I, for the life of me, don't know why. This seems like it should be such an obvious thing to do. Why on earth would it not like this? Have I done something here? Unindent does not match any outer. On line 8. On line 8. This is like an I hate Python moment for the ages because I feel like I've not done anything wrong. Like I've imported two functions here. I've imported random. And unless I'm just missing something entirely, what? 1, 2, 3, 4, 5. It's all of a sudden decided that when I hit enter, it wants to give me 5 spaces. Delete line 7. Okay, interesting. Man, I was so tilted by this that I printed the files, which are not even the file, like the file names and not even what we read in. So I've read these in, and I probably should like return these into something. I was so worried about that red. I mean, this is like as bad as Python gets because I could see you just quitting Python forever after something like this. And now it's okay. So I'm going to say what? I'm simulating an election. Maybe. All right. And so what we should say is we're reading the electoral votes, and that's going into something that we care about, which is the electoral votes dictionary. And then I'm reading in the polls from the poll file. And now I'm going to print the electoral votes. And I'm going to print the polls. All right, saved, run. Okay, and so now we see two things get printed. There's no error messages. Python does not do well with indentations and an extra space, but it does great with CSV file formatting and reading. So our sanity check, here we see Alabama is 9, Alaska is 3. Those are all the electoral votes. Then we're going to print all of our percentages too, Alabama 0.32, Alaska, and so forth. So that's our Alaska 0.472 value from before. Everything seems to be working. Yay. And now that I've got this, I did my sanity check. What should we do? All right, we should simulate an election. That would be good. So we need to set some of the other parameters. There's other things that we care about, right? We care about we've got the polls, we've got the electoral votes, but we need the number of trials. So number of trials probably makes sense to be, let's just set this thing to 1 million. So we have 1 million trials. And then the other thing we want to set is the margin of error. So I don't need a comment for that. I'm just going to say that the mo is equal to, as I said, a standard margin of error is like 5%. That's a solid poll. It's saying we have enough respondents that statistically speaking, we feel like we're within 5% most of the time of the true value. And then we want to run our simulation. So I'm going to call simulate multiple elections, and I'm going to give it the polls. I'm going to give it the electoral votes. I'm going to give it the number of trials, and I'm going to give it the mo. And as a result of this, we know what we're going to get. We're going to get this tuple of 3 things. I'll remind you that at the end of this, you get the probabilities of candidate 1 winning, candidate 2 winning, and a tie. So I'm going to call these probability 1, probability 2, probability tie equals the result of simulating multiple elections. And when I've done that, what I want to say is, all right, let's print these. So simulation run, and I'll print probability of candidate 1 winning is probability 1. And I'm going to do the same thing for probability 2 and probability tie. So I just need to change this stuff. Candidate 2 is probability 2, and probability of the dreaded tie is probability of tie. And now we're ready to run. So I picked the only thing that can change run to run is I guess I can change the number of trials, I can change the margin of error, but the data are going to stay the same except for the polling file that I use. So I'm going to use the polling file, which is early polls. That's the first set of polls that I have, I think from like June 2016, like that sort of time frame. If you run this, what do we get? That's the question. I want to come down here and run the whole thing. When we run it, what do we see? Anybody get the simulation? No one's got an answer for me. All right, well, I'm going to run it. So I'm going to run my simulation, ready to go. Say Python 3, main.py. Adam says candidate 1 wins. Let's see. I'm going to run it. It'll take a little bit of time, probably take a few seconds. It is Python after all. It's got to be a little bit slow. Simulation runs. I get 100% chance of candidate 1 winning. A 0% chance of either of these other two outcomes. Now, maybe there's a little bit of round off here, and I could print it to multiple decimal places, but I think you get the idea that we appear to have a very confident simulation predicting a Clinton outcome. I've run this before, and I'll say I didn't quite get 1.0. I usually get like 99.9%. So something really close to 100% of the time over all these simulations, you're seeing a Clinton victory. That seems a bit odd, right? That's like very confident. So you might say, well, I know that she didn't win. So what's going on here? Maybe our simulation, for example, is just too confident. And this is real polling data. So maybe our simulation is too confident. If it's too confident, then this is a sign that what should we do? We should make for a margin of error that's wider to allow for a wider collection of things to happen. So I'll change this value to 0.1. And I'm going to run it again. And it's going to take a few seconds. I probably should clean up these other things that we have. Candidate 1 wins. Now I have 100% of the time that they're winning. I feel like I might have done something here. And I wonder if I don't have like a slight issue with my margin of error. So let's see. These values look good. Everything is getting read in here correctly. So everything's between 0 and 1. In fact, I'm going to go ahead and don't need my sanity check anymore because I know I'm reading in the states and their associated number of votes or associated polling values correctly. So we won't do this. And I could even dial this down to 1,000 and do this check again. And I'm getting 100% of the time. So I bet you I've got a mistake. Let's go and let's see. We'll see if I can reason through this in real time. Shouldn't be too hard. So when we simulate the multiple elections, of course, what we're going to do is count the number of times candidate 1 wins, 2 wins, and a tie. Range over the number of trials. If the number of votes for candidate 1 is bigger than votes 2, we're going to increase win count of 1 by 1. Otherwise, we're going to increase win count of 2 by 1 if the number of votes for candidate 2 is bigger. This is be a very natural place for me to do something like that, but I didn't do that. So far, so good. And then the third case is that we have a tie. I'm also kind of worried about this indentation. This whole thing didn't make sense to me, but at least it does look to be consistently indented, so okay. And probability 1 is the win count 1 over number of trials, 2 number of trials, and tie count looks good. I'm also happy to have any thoughts about what I messed up. I'm imagining that it's probably in add noise, but we'll see. So college votes of 1 is 0. We're going to say we adjust the poll for the current polling value using the margin of error. If it's bigger than 0.5, candidate 1 wins. Otherwise, candidate 2 wins. This looks right. And then we're going to return college votes of 1 and college votes of 2. So far, so good. So that appears to be more or less right. I bet I adjusted the noise incorrectly. So I'm going to say x equals random.gauss of 1. I'm going to divide it by 2, multiply by margin of error. And then I return my polling value plus x. All that looks good. All that looks good. Built-in function. I think I called random.gauss of 1, and I don't think that's giving me what I needed. All right, we had somebody in the chat just now tell me, thank you. You let me flounder around like a fish out of water, praying I was going to be able to find it. And then you pointed out my mistake. All right. So I don't even know what this would have, let's see. I don't know what Gauss Random.Gauss of 1. I guess it's a random one. I don't even know what that's going to produce. It produces something. Maybe it's centered at 1. Whatever it is, it's not something that we want to work with. So you want to give Gauss 2 parameters. You want to give it, in this particular case, what you're giving it is, I'll just scroll down, we'll show you. Random.Gauss takes the mean, which is 0. That's very much the mean of this distribution. It's in the middle. And it needs to take the standard deviation, which is 1, which is going to ensure that, so each of these ticks is associated with 1 standard deviation. So 95% of the data are within 2 standard deviations for the Gaussian normal. All right, so now when we run the simulation, I did it for 1,000 simulations, and what we'll see, let me go back and do this again. So when we go to main, I want to run this for 0.05. Run it for 0.05. And I was a little confused as to why I was getting 100%. So they win 100% of the simulations when the number of trials is 1,000. When the number of trials is 1,000,000, we're going to need to wait a few seconds. And let's see. And here's where we see, okay, there's some chance of a tie. Fortunately, it's pretty small. Clinton wins nearly 99.9% of these simulations. So they seem to be doing very well. And I'll do the same thing that we did before, which is let's make our margin of error 0.1 to make for a more conservative estimate. And when I rerun, let's see what happens. And now we see, what do we see? Still a 98.7% chance of a Clinton victory according to these polls. A margin of error of 0.1 is pretty conservative statistically. So, I mean, if you think about our data, a margin of error of 0.1 means somebody could be at 60%, polling at 60% in a state, which is a huge lead according to the poll. But it's saying that there's, the estimated values between 50 and 70, which means if you look at this, like 2.5% of the time, somebody could be polling at 60%. But the true value would be that the other candidate is actually leading. So a margin of error of 10% would normally mean that we don't have very much confidence in this poll at all, and we're trying to really allow for a very wide category of possibilities. So when we run it with 0.1, we nevertheless get this very confident prediction in a Clinton victory. Of course, maybe she just had an early lead in the polls, right? So let's advance time and see what happens when we go to the conventions. That's the next data set I should look at. So I'm going to say data./conventions.csv. And when we run that, this is farther along in the summer before the election occurs. You might say, oh, well, I bet everything is getting closer. Here we see she's got a 99.3 or 99.4% if we round up chance of winning. So actually the lead is increased. That's what the polls are telling us here. And then we could do it for the final. I mean, we want probably the most accurate data are going to be right before the election. That's around the time of the debates. So after they debate each other, we captured polling data from then too. And you think, well, certainly this must have become closer. And yet when we run it, what we get is a 99.6% estimated probability of a Clinton victory. So we're more confident than we've ever been, even with a 10% margin of error in our polls, that this one candidate is almost certainly going to win. Now, that doesn't mean that it's impossible, but we're predicting a 99.6% chance of their victory right before the election. or let's say a month or so beforehand. And that means that given how this actually turned out, we probably should reflect a little bit before we stop. We've written all of the code that we're going to write, but we should at least take an opportunity to reflect on the simulation itself because, well, let me show you what real election simulators produced during this time frame. So real election simulations during this same time frame. The top one is 538, popular media outlet, and the bottom one is the New York Times. And as you can see, so blue is the likelihood of a Clinton victory based off of the state polls. Red is Trump. They both follow this same sort of shape. I guess it's like a Rorschach test if you turn your head and try to figure out what that looks like. But they both have the same general type of shape. And yet, when we look at this shape, they're both confident in a Clinton victory, and yet they're not as confident as what we were, even with this margin of error of 10%, which was pretty conservative. We were estimating like a 99-point-something% chance of a Clinton victory throughout this entire process. Their estimates were much more conservative even than ours. New York Times was sort of a little more conservative, and 538's was very much more conservative. At one point in August, they had the race being essentially a coin flip before they diverged a little bit again. And the question that I would have for you is, why? Why is it the case that even with what we think is a conservative estimate, the national media outlets produce these estimates that are even more conservative, that show a closer race than what we might estimate? Why is that, do you think? Yasmin says biases. Okay, I like the thought, but bias of what precisely? One thing, maybe there was a late swing towards Trump, but even if you looked at the polls that were taken a few days beforehand, they were still in line with this idea that there was a predicted Clinton victory. You can never be 100%. We'd love to have a larger data set. We used the same exact data that 538 had. One of the things they did, which was great, was they said, here are the polls that we used. Here's where you can go and download them. So that's what we did. We just went and downloaded them. We just didn't capture like as much granularity as they did. We figured 3 time points was probably reasonable. Maybe we oversampled people. This is getting at a really good one. A really good point here is some of the polls are more or less reliable. And that doesn't mean that they're necessarily consciously biased, although if a poll has a lot more respondents, it's going to be more reliable. But also certain media outlets, for whatever reason, have long been known to estimate outcomes based off of polling in one direction or another, whether it happens to be slightly biased towards Republicans or slightly biased towards Democrats. And so one of the things that especially 538 did was it assigned a poll grade based off of the number of respondents, based on sort of the history of this media outlet and how accurate they tend to be with polling. So that's really good. There's a variable not captured in the simulation. I like that a lot. I don't know what you're referencing. What I would say is there very much is a variable not captured in the simulation, and there's a way I'm going to put that here in a second, but you're absolutely right. That having been said, it was not captured. What I'm going to get at was not captured in either of these as well. So I'm going to say something about what this is not capturing. It's not as if our simulation is inherently worse than what either of these simulations are. There's 2 more things that they do that we don't do. I think you look at these and think they must be very sophisticated, right? I wrote, 5 functions to write an election simulator, and it's not reflecting what these polls are doing. So it certainly must be the case, and especially because these are so prominent, they must be fantastic, right? They must be hundreds of thousands of lines of code long. And I'm here to tell you that the answer to that is very much no. So there are a couple things that they do that we don't do. One of the things that they do is, when I showed you this distribution, the notion was 5% of the time you'd be outside of this range, or between -2 and 2. So it allows for these events to happen outside of this range, but they're not tremendously likely. When they do these simulations, whether it's 538 or the New York Times, I believe they used a distribution with a little bit fatter of a tail. So that's the fancy term, technical term, for meaning that there are values in a fat-tailed distribution that are more outliers. So it allows for outliers with a greater probability. And if you have fatter tails, it means that you're allowing the poll value to adjust in a greater collection of directions. That's one of the things that they did. That would not be hard for us to change. We could just change, instead of sampling from a standard normal, we could sample from like a t distribution. That wouldn't take that much time. There's one other thing, like digging into their model. They do a couple things, but really, the only main thing that they do that was different, at least in 2016, although who knows how much they changed these, because these were just so woefully off. But they noticed that if there is systematic bias, it's probably going to influence states that tend to vote similarly. So if there is something that we're missing in the data, that's going to push the true outcome of the election in one candidate's favor versus the other, then states that tend to vote similarly are going to see those results, that bias, correlated. So as a result, we know for a fact from this election that Trump won a lot of the Rust Belt states, and sort of across the Midwest in the United States, Pennsylvania being one of those. And that's because, a lot of those Rust Belt states correlate in terms of how they vote. So another one, for example, Minnesota and Wisconsin, they're near each other, and it tends to be the case that whichever direction the poll is leaning or it may be biased in, these two states are going to vote similarly. And so they noted that and said, if they're missing something, then as a result, anything that they're missing that's systemic, that applies across the entire poll, is going to have states' outcomes be correlated. And what we did when we ran our simulation and we captured a value from the polls, like I looked at early polls, we took Minnesota and we adjusted it in a certain direction. And then we took Wisconsin and we adjusted it in a certain direction. And those two adjustments were completely independent. Wisconsin could have gone up and Minnesota could have gone down, or vice versa. Whereas in practice, what they're saying is, when you adjust the poll, whichever direction you adjust Wisconsin in, up or down, you probably should adjust Minnesota up or down in the same direction. That's a really good idea. That's really the only thing that's kind of essentially missing from what we did. And we could take the time to go and do that and add correlation to the polls when I write add noise and make sure that this is represented across the states. You would be more than welcome to do it yourself, but we're not going to do that and bring it up to speed with something that's published in a national poll. And the reason is that there are still some things that are just missing. There are two things I want to point out. So, number one, the big thing that's missing is, imagine a circumstance where one candidate is polling at a higher percentage than the other candidate, but the underdog's followers happen to be more enthusiastic. So they attempted to capture this in a Los Angeles Times poll that was running through this entire period of time. It was called the Daybreak Poll. And it weighted the respondents' selections based off of also how enthusiastic they were about the candidate that they said they were going to vote for. And this was a major outlier throughout this entire 2016 process. And it was showing this 46% towards the election day, 47% estimate for Trump, And no other poll was showing this sort of estimate. It was also a ludicrous poll from another perspective, because this was a national poll. They didn't bother to try and do this on a state level. I'm sure that would have taken a lot of resources, but the whole election simulation has to depend on the states because of the Electoral College. Without the Electoral College, you're not, you have to simulate what it is that you're simulating. So the idea is that probably, especially not everybody's going to vote. If you call a random person, you might just be calling somebody who has a weak sentiment or isn't actually going to show up to the polls. And if you have one candidate that has more enthusiastic voters, they're more likely to show up at a greater rate. That was a good idea. It's not present in our poll, and it's not present in either of these other polls or either of these other simulations. The other point I want to make is a math point. So that's like a human level point, but then there's a math point too, which is I want you to imagine that a meteor, like look at a value like right here or right here. And I want you to imagine that you turn on the weather and the meteorologist says there is an 80% chance of rain in 3 months. 3 months from now on a certain Monday, there's going to be an 80% chance of it raining on that day. Would you believe them? Would you believe that meteorologist? And what am I getting at with asking that question? BZ, very trusting. You're just going to believe the meteorologist? Okay, fair enough. I don't know that I would. 3-month forecast? I don't know if there's any weather person in the world that's that good. Why is that a hard thing to do? Yeah, anything that far away from an actual event has an enormous amount of uncertainty. As we've seen, global events can dictate major changes in these sorts of things. And the point with the weather is that ultimately, well, both elections and weather are extremely volatile. So if we look at this, we might say, well, just trusting something that's happening in August and saying at this point in time, we're 80% certain that a certain candidate is going to win, that's missing a huge amount of volatility and everything that can happen in the meantime. So probably most of the time, if somebody were saying, I think there's only a 20% chance of this other person winning and we're 3 months away, you should probably bet some money on the other person. That aside, the point here is, what should we do? It seems like we built a nice model. Like we created this cool simulation. We used Monte Carlo. We started with a casino example, and we saw that that same paradigm will allow us to build something that is really only this away from being able to make something like this. So we wrote here 150 lines of code. We're probably another 100 lines of code from doing exactly what 538 did, which wound up getting many millions of dollars of funding, I think, and was like a national media market for a period of time. But the issue is, what do we do? What do we do at the end of the day? And yeah, we could try to make a better, more confident prediction. But if we're ultimately saying, I don't know, it's hard to say 3 months out with any sort of certainty. And a lot of people are saying a better model might start with things very much closer to 50% and then only have confidence in the predictions once we get closer to the date itself. So in that model, we would essentially say, I'm just going to shrug and I'm going to say predicting the future, especially when we're dealing with a volatile event, that's hard. But the problem with that, the ultimate problem with that, is that there's no money in that. And that's what we care about, because we have to make money. So that's what we're going to go with our idea number 2. Our idea number 2 is, if we can't build a pretty model because predicting the future is hard, then we're going to turn it into a market. That's what America does the best anyway. And so we're going to say, why don't we just open this market to the world and say, whoever you think the next presidential election is going to be won by, you can make a bet on it. So here's for the website Kalshi, here is the prediction market for the 2024. Oh, we're already in 2026, the 2028 presidential election. I've lost track of time. That's happened post-COVID. But for the next election, you can say, and you can bet, either in favor of the candidate that you think might win or against them. So you can wager against a certain person or in favor of the certain person. You can imagine this might be very useful to you in a lot of different ways. So if there's someone that you see that you particularly don't like, maybe you wager on them so that then if they do win, you kind of hedge your outcome. And here are the collection of people that are available for, at least on Kalshi, for 2028. One of the things that I think was hopeful about this is this allows you to not run any models at all, or you could have multiple different people run a bunch of models, and then they could invest money in this. And then at the end of the day, it would tell you, oh, this is what the true probability is, because this is what the market is dictating that it's going to be. All that being said, some of these, and they've had celebrities on here that were at like 3 or 4%. It seems like they've cleaned some of this up. But at one point in time, there were some truly ridiculous people that they had on here that you could get for like 3 or 4%. So even though we're saying, oh, we'll let the market decide, that doesn't necessarily produce a correct outcome. So that's one major issue with this. The other major issue, and I wanted to make this transition to talk a little about prediction markets on the whole, because it's a completely different way of coming at predicting the future. One of the ways of doing that is to run a bunch of Monte Carlo simulations and take the average case behavior. We've seen that with volatility, that can be a little challenging, as well as the fact that you might not just be missing something in your data. Your data might be systematically biased. Whereas if you turn this into a market, maybe it's the case that somehow the market just figures everything out. And so at this point in time, well, what is it saying? It's saying J.D. Vance is the favorite, then Gavin Newsom, then Marco Rubio, and all of these change over time. We're producing a 538-like plot where you can wager on this, and then at any point in time, this is telling you what the percentage chance is, and so you can make money off of this if it's correct. Now, you're going to have to wait a long period of time. I think you actually, on this platform, you earn interest in the interim. But then you say, well, does this mean I could prediction market everything? I don't need to simulate anything. So I could simulate the weather, or I could just bet on the weather. And we get stuff like you can wager on the number of tornadoes this month, or in a particular region. You can wager on the high temperature of the day and all kinds of stuff. So this has become very popular these days, but it's not new. It's just becoming more prominent. So there is a notable example of this from 25 years ago, when after 9/11, the U.S. government thought, if prediction markets are neat, why don't we make a prediction market around terrorism and assassinations? So it might sound pretty dark, and that's because it is pretty dark, but maybe we'll just let the market tell us when the next terrorist attack is going to happen or an assassination is going to happen. And then people said, well, this is really, really bad because there are a million reasons here why you probably should not be doing this, even though you're using it as like an intelligence thing. Just imagine how, it's bad enough we're wagering on tornadoes, but we'd be wagering on terrorist attacks too. It's hard to believe that this was ever really taken seriously for a moment, but it was. And there's other weird things with this. So I guess we were talking about Super Bowl halftime in our prelims today, and I don't want to have to subscribe. Okay. There was a big discussion and conflict about this because you can also place these contracts on a lot of stuff associated with sports, and then meta things associated with sports. So if you love the Bad Bunny halftime show, well, you actually could have bet on a lot of things associated with it. And one of the things you could bet on was Cardi B part of the show? Or did she perform during the halftime show? So at the end of it, it seems like a simple question. Either she did or she didn't. And then there was a question of, well, yeah, she wasn't on a microphone, but she was very clearly visible in the background of the Bad Bunny performance. And you could see that she was like singing along. So does that count as a performance? because you're dancing and you're on camera and it's clear your lips are moving. And then it became a big issue because some of the prediction markets said, we're going to resolve all these to yes. Others said, we're going to say no. And then it becomes a controversy because it's such a borderline call. And then you're starting to think, well, is this gambling? That's my question to you. Is this gambling? BZ says, seems like gambling. Okay. Lori, I'd say so. Another looks like. Another yes. A lot of votes for yes that this is gambling, because after all, you could buy a contract on who won the game. That's the other stuff that is on here. There's sports. And so there's games that are in progress right now, and you can purchase contracts on Kalshi associated with which team you think is going to win or lose the game, right? That seems like it kind of smells like gambling, but this is something that is very important, that all of the law ensures that I have to assert, which is that Kalshi is not gambling. And I have to make sure that I type this out a lot of times, just so that I'm completely 100% confident that I know that Kalshi is not gambling. It's a prediction market where you're able to buy contracts. Kalshi is not gambling about the future. And anytime I want to call it gambling, I have to make sure that I come back to this and type out that it's not gambling. Because if it's gambling, well, then that means that it needs to get regulated like gambling is, and it's not in the US. And that means that, well, you might have to face the consequences of what gambling is. Because if it's gambling, right, well, who is that going to hurt? Who is gambling? Who is gambling always going to hurt? It's always going to hurt the young men. They're always the ones who are going to get sucked into things like gambling addiction, which is something that we saw in the crypto era and all this sort of thing. And so it's a good thing that Kalshi is not gambling, because if it were, you'd have all these sorts of problems. I know I love it. I've said I love fracking. I also super love Kalshi. And I know for a fact I can not bet is the wrong term. I can purchase contracts on a lot of different outcomes. And one of the ones that I looked at the other day, in fact, I put a little $10 bet of my own on, was it seemed like Giannis was going to leave the Milwaukee Bucks. And that was really something that I thought, well, I know a little bit about basketball. I know which team is probably the best fit for him. So this is something that I could make a wager on. Oh, Kalshi's not gambling. I could purchase a contract about what his next team might be. And of course I didn't win that. Right, I definitely didn't win it. And then it was interesting because then I logged onto Twitter, which was a bad decision because it's not a very good place these days. But I figured, well, I'll check out Twitter just to see what's happening over there. And everybody was so upset. Because then I saw this post where Giannis says, we're all on Kalshi now. And like 12 hours after this market has resolved that he had asked for a trade and said he wanted to leave, and then somehow he just wound up staying, he then came out as a shareholder in Kalshi itself. So that's okay. You know, at the end of the day, this is, I think it's pretty clear. This is not a conflict of interest or anything like that. Kalshi is very much not gambling. It is a wonderful company. I love it so much. But more than that, I love coding, and I love you all too. So that's it for today. I can't wait to do what we do next, which is we're going to take a look at some other really cool stuff, from building cellular automata that can self-replicate. We're going to look at gravity simulations. We're going to make evolutionary trees. We're going to go to the moon. I want my $10 back, but that's all right. I'm probably not going to get it. I'll see you next time. Until then, happy coding.